Welcome back to the Code Navigators. Our mission here is to transform the massive, intimidating volumes of the International Code Council documents into clear, useful knowledge. Whether you're actively studying for an ICC exam, trying to find that one specific table, or you just need a really thorough, focused understanding of a chapter, we're here to guide you.
We're basically turning overwhelming text into a navigable map.
Exactly.
And today, we are undertaking a critical analysis of one of the most important chapters in the 2021 International Building Code, the IBC.
We're jumping into Chapter 18, Soils and Foundations.
Yeah, and this chapter is absolutely non-negotiable. It governs the most fundamental part of any building, the connection between the structure and the earth itself.
If you get this wrong, it doesn't matter how well the rest is built.
Not at all. The entire building can fail, regardless of how good the design is for everything above ground.
Okay, now, well, before we jump in, we need to address two critical notes. First, about how we put this together. The core analysis you're about to hear is generated with the help of advanced artificial intelligence. But, and this is the important part, the process is always meticulously overseen and reviewed by a qualified human code professional.
That's me. And my job is to ensure accuracy and, contextual relevance.
And that leads us right into our crucial legal disclaimer.
Yes, this serves as the bedrock for our entire session. This content is strictly for educational purposes only.
We're here to help you understand the structure of the code.
Right, to explain the concepts and help with your study methods. It does not, under any circumstances, constitute professional advice or engineering consultation for real-world projects.
That is so essential. You must always consult the official current ICC code edition, in this case the 2021 IBC, along with any local amendments.
And critically, a qualified professional, a registered design engineer, an architect, someone licensed to do this work.
We also want to affirm that throughout this, we will not be stating any copyrighted material from the official code text verbatim.
We're just analyzing and explaining the core concepts.
Okay, with that said, let's look at Chapter 18.
So think of it as the complete instruction set for the foundation system. It provides criteria for geotechnical considerations, that's the science of the soil, and the structural side of things.
So how to select, design, and install a foundation system that can actually support the building.
Exactly. A system that can reliably support all the loads imposed on it, from simple gravity to, wind and seismic forces.
All right, let's start at the beginning. Part 1, General Provisions.
Okay, so we're in Section 1801, the general scope.
This is a quick but essential read.
It is, because it makes it crystal clear that the provisions of Chapter 18 apply to all building and foundation systems. No exceptions.
It's the governing framework for literally everything that touches the ground.
Yes, and it does more than just state its scope. Section 1801 really sets the stage for all the specific criteria that come later.
Things like geotechnical investigations.
Right. Or the required depth for frost protection, the critical rules for preventing water intrusion. It's basically telling you, the designer, that you have to address all these different factors.
Okay, so that moves us right into Section 1802, the design basis.
And this is the core mandate for structural safety.
This is what it's all about.
It is. The code requires that foundations must be designed to safely transmit the structure's loads, which, we learn all about in Chapter 16, down to the supporting soil or rock.
And the design has to use allowable bearing pressures and stresses that are determined either by the methods laid out later in this chapter,
or by alternative, what they call performance-based design methods.
And that point about alternative methods is really key for understanding how the IBC works, isn't it?
It's crucial. It shows the code's hierarchy. If a designer chooses a more rigorous, performance-based approach, maybe for a really complex high-rise building, they have to design the structural elements, including the foundations, according to the provisions of ASE 7.
Specifically, Section 2.4 of that standard.
Right. So it highlights that the IBC is the governing document, but it frequently defers to widely accepted engineering standards like ASE 7 for the really detailed structural calculations.
That cross-referencing is a perfect example of why code navigation is so important for studying. You have to know that Chapter 18 starts the conversation, but Chapter 16 on loads and standards like ASE 7 provide the detailed math.
Exactly, and the cross-referencing doesn't stop there. Section 1802.1 clarifies that the actual materials you use in the foundation, think reinforced concrete, steel piles, masonry walls, have to comply with the rules in other major chapters of the IBC.
So if you're designing a reinforced concrete footing, Chapter 18 tells you how big it needs to be based on the soil and the load.
But Chapter 19 for concrete gives you the material standards for the concrete mix and the rebar itself.
And it's the same for other materials. Masonry walls point you to Chapter 21, steel to 22, and wood to 23.
It's the code book establishing a partnership. Chapter 18 is like the lead engineer laying out the foundation requirements, but it relies on those other chapters to make sure the concrete or steel is actually strong enough to do the job.
It prevents the code from becoming impossibly repetitive.
You got it. Otherwise, you'd be listing material standards in every single chapter.
Okay, let's move to the geotechnical heart of the chapter.
Section 1803, required geotechnical investigations.
This is where the code tells us we can't just guess or use those assumed values. Sometimes you have to hire a specialist to analyze the ground.
Right, and this investigation is mandated for complex projects, sites with known poor soil conditions, or any time deep foundations are on the table.
The code is also very specific about who does this work.
Oh yeah. Section 1803.2 mandates that the whole investigation, the procedures, the equipment, must be overseen and performed by a registered design professional.
So, a geotechnical engineer.
Typically, yes. And they have to have a fully qualified representative on site during all the boring or sampling operations.
Why is that so important?
Because the observations they make while drilling, how the soil behaves, what it looks like coming out of the ground, are just as critical as the lab results that come later.
And what are they looking for? Section 1803.3 defines the scope, right?
It does. The investigation has to accurately determine the soil profile, what layers are down there. It has to locate any existing fill materials that might be unsuitable, and then it has to quantify the actual allowed capacity of the soil.
So it's a comprehensive look at how the earth is going to behave under the weight of the building.
A very comprehensive look. It includes checking for compressibility, liquefaction potential, especially in seismic areas, and the potential for the soil to be expansive.
A critical step here is soil classification.
Absolutely. Section 1803.5.1 mandates that all the soil materials have to be classified in accordance with ASTM D2487.
And that's the Unified Soil Classification System.
Right. And this ensures that when a geotech engineer's report says CH, which is high plasticity clay, every structural engineer who reads that report knows exactly what material they're dealing with, no matter where they are. It's a common language.
Section 1803.5 then focuses on the site-specific dangers, the questionable soil conditions that trigger a mandatory investigation.
Right, even if the building is otherwise pretty simple. This includes things like expansive soil, high water tables, or soils that just seem to have really low bearing capacity.
Let's talk about expansive soil, because that's a big one. It's in 1803.5.3.
It's huge. It causes billions of dollars in damage every year in the U.S.
So what is it doing?
These are soils that swell up dramatically when they absorb moisture, and then they shrink when they dry out. This constant movement can literally heave, lift, or crack foundation slabs and walls.
So how does the code define what's an expansive soil that needs special treatment?
It gives 4 specific testing criteria. First, a plasticity index, or PI, of 15 or greater. Second, more than 10% of the soil particles have to pass the number 200 sieve. Third, more than 10% of the particles have to be smaller than 5 micrometers.
And the fourth?
An expansion index greater than 20, which is determined using the ASTM D4829 standard test.
Okay, let's unpack what those 4 tests actually mean. The plasticity index.
The PI measures the range of water content over which the soil acts like a plastic, like putty. A high PI means high clay content and a high potential for swelling.
And the sieve and micrometer criteria are just confirming it's a fine particle soil.
Exactly. You're confirming it's got a high percentage of very fine particles, clay and silt, which are the components that actually absorb the water.
And then the expansion index test is the final proof.
That's the direct physical test that actually measures the soil's potential to change volume. So the code uses this layered approach. Confirm it's clay, then confirm that that clay is, in fact, highly expansive.
Makes sense. Another major trigger is groundwater.
Yes. Section 1803.5.4 requires the investigation to determine the location of the groundwater table, specifically if it's at or within 5 feet of the lowest floor level.
Why 5 feet? What's the magic number there?
Because a high water table is the precursor to hydrostatic pressure. That means water is pushing on the foundation. And if you have that condition, your design has to immediately defer to the really stringent waterproofing requirements we'll see later in Section 1805.
Okay, and what if the project needs deep foundations, like piles or drilled shafts?
Then Section 1803.5.5 adds a huge layer of complexity to the geotechnical report. The report has to provide crucial operational data. This isn't just about soil capacity anymore.
This is about installation logistics.
Completely. We're talking about things like recommended deep foundation types, the mandatory center-to-center spacing to avoid group effects, specific driving criteria for driven piles, detailed installation procedures.
So it's basically the instruction manual for the contractor.
It practically is. It has to include field inspection protocols, load test requirements, and even the suitability of the foundation materials for that specific subsurface environment, especially if it's corrosive.
And all this work culminates in the report itself, Section 1803.6, reporting requirements.
Right. And that final report is a crucial document. It has to be submitted to the building official with the permit application.
And it has a long list of mandatory elements.
A very long list. A plot showing the precise location of all the borings and tests, a complete raw record of the boring logs, the elevation of the water table, and comprehensive design recommendations.
And those design recommendations are critical. They have to specifically address how the proposed foundation is going to handle things like expansive soils, liquefaction, differential settlement, and the expected lateral soil loads.
That report is the foundational legal and engineering document that justifies the design choices.
So, we've investigated the site. Now we get to the physical work in Section 1804, excavation, grading, and fill.
And the first safety mandate in 1804.1 is about protecting your neighbors.
Right, you can't compromise their buildings.
Any excavation must not reduce the vertical or lateral support for an adjacent foundation unless that structure is underpinned first. You just can't compromise the stability of existing buildings.
And underpinning, which is supporting an existing structure while you dig below it, is covered in 1804.2.
It is. And that work has to be designed and installed according to approved documents. And importantly, it has to comply with the general safety and site work rules found in Chapter 33.
So foundation work often crosses into temporary construction safety rules.
Frequently. Then, when it's time to put the soil back, 1804.3 details the placement of backfill.
The material has to be clean, no debris or big rocks.
Right. And there's a specific note here about something called controlled low-strength material, or CLSM.
Flowable fill.
Exactly. It can't be used as backfill around a structure unless that structure is specifically protected by waterproofing or damp-proofing, according to Section 1805.
Yeah.
The code treats it differently than compacted soil.
Now, one of the most common problems I see on site inspections is poor grading.
And 1804.4 tries to prevent that. It mandates that the ground immediately next to the foundation must slope away from the building.
The minimum is a 5% slope for at least 10 feet out.
Right, which is 3,048 millimeters. And this is arguably the most effective, simplest defense against water intrusion.
It's all about directing that surface water runoff away.
Prevents saturation of the soil right next to the wall and reduces hydrostatic pressure. There is a practical exception, though.
For tight lots, like in a city.
Exactly. If lot lines restrict that 10-foot distance, or if the climate or soil is unusual, the building official can approve alternatives, like swales or specialized drains.
But you still need some slope.
Even with an alternative, the surface still needs a minimum 2% slope away from the foundation within the first 5 feet.
Section 1804.5 then deals with a really serious hazard, flood hazard areas.
If you're grading or placing fill in an area that's subject to flooding, the rules get way stricter.
Any fill placement requires a specific engineering analysis.
Yeah, often involving hydraulic modeling to make sure that the fill you're adding doesn't make flooding worse, either on your property or for your neighbors. That could violate federal flood regulations.
And what about the fill itself? If we're using compacted fill?
That's an 1804.6, compacted fill material. This ensures structural integrity when you have to replace the original soil. The placement is highly regulated.
The maximum thickness of any single layer or lift is 12 inches.
305 millimeters. And that limit is there to make sure the compaction equipment can effectively densify the entire layer of material.
And you have to verify that compaction.
You do. Once it's compacted, the material has to achieve a minimum density of at least 90% of its maximum dry density, as determined by lab tests. This field testing ensures the engineered fill can actually bear the loads without settling down the road.
Right, we built the foundation, we've compacted the soil, now we have to protect it from its biggest enemy.
Water, Section 1805, damp proofing and waterproofing.
And the distinction between those two is really important.
It's critical, both conceptually and for what materials you choose. Damp proofing is used to prevent the intrusion of just ambient soil moisture, think humidity or water vapor, where you don't expect hydrostatic pressure.
And waterproofing is for when you do expect pressure.
Exactly. It's required when that subsurface water investigation we talked about shows a high water table exists, meaning hydrostatic pressure is expected.
So dam-proofing is like a rain jacket.
Good analogy. It blocks light moisture absorption. Waterproofing is like sealing the entire foundation wall as if it were a swimming pool, resisting actual pressure from standing water. It requires robust, continuous membrane systems.
And Section 1805.2 specifies the materials you can use.
Right. For concrete and masonry walls, you're looking at things like polymer-modified bituminous material, bentonite clay, or synthetic membranes.
And for concrete slabs.
The code mandates a vapor retarder, usually a sheet of plastic, like a 6 mil polyethylene sheet placed between the subgrade and the slab to block moisture from migrating up from the ground.
And to make this all work, you need a drainage system.
Section 1805.4 mandates a subsoil drainage system, unless the soil is so naturally porous, like clean sand or gravel, that it's not needed. The whole point is to collect subsurface water and eliminate that pressure against the walls.
The design is pretty prescriptive.
It is. The drain has to be installed at or below the level of the floor slab. It has to be protected with a filter, material like gravel, or a geotextile fabric to keep it from clogging up.
And it has to discharge somewhere safe, away from the building.
Of course.
Okay, let's shift gears from water to structural capacity. Section 1806, presumptive load-bearing values of soils.
This section offers a shortcut. If a full geotechnical investigation isn't required under 1803, meaning the site is simple and not hazardous, the designer can rely on these assumed or presumptive allowable bearing pressures from Table 1806.2.
It's a trade-off, right? Simplicity for a big factor of safety.
A huge factor of safety because the assumptions are so broad.
Let's use that table to show how important soil classification is.
Okay. If you're lucky enough to build on crystalline bedrock, the maximum allowable vertical bearing pressure is 12,000 pounds per square foot.
Which is massive.
Massive capacity. But if your soil is classified as soft clay, that value plummets to 1,500 PSF.
That's an 8-fold difference.
An 8-fold difference in capacity, which directly translates to an 8-fold difference in the size of the footing you need to support the same load. It's a huge deal.
And the soil doesn't just hold the building up, it resists lateral movement.
Correct. Section 1806.2 covers lateral load resistance. Foundations have to resist horizontal forces from wind, seismic, or sloped ground.
And they do that using two mechanisms.
Friction between the foundation and the soil, and lateral sliding resistance, where the footing pushes against the soil next to it. Table 1806.2 gives you the coefficients of friction you need for those calculations.
The code even allows for some optimization here.
It does. Section 1806.3 allows for an increase for depth. If a foundation is located deeper than 12 inches below the finished grade, you can modestly increase the presumptive bearing pressure up to a certain limit.
Because deeper soil is generally more stable.
It's more confined, so it offers better capacity.
Okay, that brings us to Section 1807, which is about the walls themselves.
Foundation walls, retaining walls, and embedded posts. The foundation walls themselves are structural elements. They have to support the vertical loads from the entire building and resist the lateral soil loads from the backfill.
And for common light frame construction, the code gives us these great prescriptive options.
Yes, to eliminate the need for full engineering on the walls. Section 1807.1.6.2 and its tables govern the minimum vertical rebar size and spacing for reinforced concrete foundation walls.
For an exam, knowing where those tables are is key.
It's a huge shortcut. You can quickly answer design questions just based on the wall height and the amount of unbalanced backfill.
And there's a similar table for plain masonry walls.
Table 1807.1.6.3. It dictates the minimum wall thickness based on height and backfill. For example, a 7-foot wall with 7 feet of backfill might need a 10-inch solid wall, depending on the assumed soil pressure.
Section 1807.2 then pivots to retaining walls.
Which are different. They're freestanding structures designed purely to hold back soil.
So they have to be designed more rigorously.
Much more. For stability against overturning, sliding, and excessive foundation pressure. For critical retaining walls, you often need a specialized geotech investigation. You can't just rely on the presumptive values.
And we can't forget about things like deck posts.
Right, embedded posts and poles, covered in 1807.3. The code limits how much you can rely on friction along the side of the post to resist lateral loads.
It's limited to 1/2 the normal force.
Which is a built-in conservatism because friction can be unreliable under cyclic loading.
And for figuring out how deep to bury these posts, there are two different scenarios.
Yes, the first is in 1807.3.2.1 for unconstrained posts. These are free to move at the ground surface like a typical deck post.
And there's a specific calculation for that.
There is, equation 18:1, to find the depth needed to resist the lateral load. We won't get into the math, but the equation is there for that purpose.
The second scenario is for constrained posts.
Right. In 1807.3.2.2, these are elements where you have lateral support at the ground surface, like a post embedded in a rigid floor slab. Because the movement is restricted at the top, a different, often shallower embedment depth can be calculated using a separate set of equations.
Understanding that difference between constrained and unconstrained is key to navigating this section.
Absolutely.
Okay, let's move into the specific design requirements for shallow foundations, which starts in section 1808.
Right, and these are defined as foundations resting directly on the soil near the ground surface, like your typical spread footings or mat foundations.
Section 1808.1 lays out the general requirements.
And there are three core conditions a foundation has to satisfy. First, adequate bearing capacity, it won't punch into the ground. Second, acceptable settlement, it won't sink too much overall.
And third, and most importantly, acceptable differential settlement.
That is the big one. That's when one part of the foundation settles more than another. It causes racking, cracking, and serious structural damage. Preventing differential settlement is the structural engineer's primary goal.
That focus on stability continues in 1808.3, design loads.
Yeah, foundations have to be robust enough to handle all the structural loads, wind, snow, seismic, plus those environmental effects like settlement caused by expansive soils or frost heave.
Speaking of expansive soil, its remediation is detailed in 1808.6.
It is. If expansive soil is present and it's expected to damage the structure, the code requires specific, approved procedures for either removing it or stabilizing it.
And these are professional engineering tasks.
Oh, absolutely. This might involve digging out all the bad soil and replacing it with non-expansive compacted fill, or stabilizing it with chemical treatments like lime injection.
And any fill you use has to meet those strict compaction requirements from section 1804.6.
You can't just dump material in a hole and call it good. It has to be properly placed and compacted.
Now, here's where Chapter 18 gets into site safety geometry, which is crucial in hilly areas.
Section 1808.7, Building Clearance from Slopes. This section establishes critical safety margins, requiring buildings to be set back a minimum distance from both the top and the bottom of slopes.
Let's look at the two scenarios. First, Section 1808.7.1, clearance from ascending slopes. This is where the building is at the bottom.
Right, and the horizontal clearance from the structure to the toe of the slope has to be at least half the height of the slope. We'll call the height h, so h divided by 2.
But it can never be less than 15 feet.
Correct. 4,572 millimeters. That h/2 rule ensures the building is outside the probable failure plane of the slope if a landslide were to happen.
And the second scenario, 1808.7.2, is for descending slopes. The building is at the top.
Here, the clearance from the structure to the top edge of the slope has to be at least 1/3 the height of the slope, or h/3.
With the same 15-foot minimum.
Same minimum. And the reason it's h/3, which is less conservative, is because the risk of the building being undermined by erosion is typically lower than the risk of it being crushed by a downhill failure.
Okay, that makes sense. Section 1808.8 then gets into the specifics of concrete foundations.
Yes, the code specifies a minimum required compressive strength for the concrete mix, which is denoted as F'(C).
And you find these values in Table 1808.8.1.
You do. For typical foundations not in the highest seismic categories, the minimum compressive strength is 2,500 pounds per square inch, or psi.
But that requirement jumps up for more demanding situations.
It does. For precast-driven piles, that minimum strength goes up to 4,000 psi. And for specialized elements like micropiles, it jumps even higher to 5,000 psi.
Because those elements carry more concentrated loads and are subject to higher stresses during installation.
Exactly. They need a more robust material.
Okay, continuing with shallow foundations in Section 1809, we have stepped footings in 1809.3.
A very common site condition. When footings have to accommodate a sloped grade, they have to be either perfectly level or stepped.
And there's a limit to how steep those steps can be.
There is. The ratio of the vertical step to the horizontal step can't exceed 1 unit vertical in 10 units horizontal.
A 10% slope.
Right. This limits the stresses caused by abrupt changes in the footing.
Then we get to 1809.5, frost protection.
A rule that is very geographically dependent, but it's universal in the code. Footings have to extend to a minimum depth below the frost line that's established by the local jurisdiction.
And if they haven't set one?
Then the minimum depth has to be at least 12 inches below the undisturbed ground surface.
And the whole point here is to prevent frost heave.
Right, you're placing the footing below the depth where soil moisture freezes and expands, which can lift and damage the foundation during the winter.
There is a pretty important exception to this for light frame construction.
There is. A structure in risk category 1, or a detached house not in a high seismic area, can sometimes be exempt from full-depth frost protection if specific criteria are met.
This usually involves things like having a decent eave projection to shed water away.
And having the foundation enclose a heated interior space, which keeps the soil right under the footing from freezing.
Finally, we get to section 1809.7, which is a gold mine for builders.
Prescriptive footings for light frame construction. This is an extremely valuable resource because it gives you minimum footing widths and thicknesses when a geotech investigation is not required. It's the ultimate simplicity option.
This all relies on table 1809.7.
Entirely. The required size is determined just by the number of floors the foundation supports and the expected soil capacity. For example, a foundation supporting 2 floors might need a 15-inch width and a 6-inch thickness.
It's the code providing a safe, assumed minimum standard for typical residential construction.
And it streamlines the permitting process significantly.
Okay, let's move into the most structurally complex area of the chapter.
Section 1810, deep foundations.
This applies when the soil near the surface just can't support the load.
So you have to rely on stronger, deeper soil or rock layers using things like piles, caissons, or drilled shafts.
Section 1810.1 sets the stage.
It does. It requires that all deep foundations have to be designed and installed according to this comprehensive section. This includes specific rules for managing settlement, accounting for group effects.
Which is where closely spaced piles can interfere with each other.
Exactly, and ensuring the structural integrity of these long, slender elements.
The design and detailing requirements in 1810.3 are pretty rigorous.
Very. The design has to account for the intricate relationship between the soil and the structure, what we call soil-structure interaction. It has to apply the right load combinations, including severe forces from earthquakes.
And the lateral loads and moments that happen when a tall building sways.
A critical part of the calculation is section 1810.3.2.3, which establishes the allowable loads. The maximum allowable stresses are highly restricted by table 1810.3.2.3.
And it depends heavily on the material, concrete, steel, or timber.
Right. For example, for a cast-in-place concrete pile under compression, the maximum allowable stress is typically defined as 0.4 times the specified compressive strength, or 0.4 F'(c).
That limit, 0.4 F'(c), is the code's way of ensuring a massive safety factor against the material itself failing.
A massive factor of safety. This section outlines complex calculations for determining these allowable loads. For navigating the code, you just need to know this table exists, and it governs the material stress limits.
And because deep foundation behavior is so complex and hard to predict.
The code, in section 1810.3.3, mandates load test methods to verify the actual performance and capacity of the foundations in the field.
These are highly specialized field operations.
Very. The code permits several approved methods, like the Davison offset limit or the Brinch-Hansen criterion. Each of these gives engineers a method for defining what constitutes failure for a deep foundation element when it's being tested under a massive load.
The code also addresses uplift resistance.
In 1810.3.3.1, this is a huge factor in wind and seismic design. The allowable uplift capacity can be determined by field tests or by specific empirical formulas. But the code requires a double check.
So it adds redundancy to the safety calculation.
Precisely.
Now let's talk about the reinforcement, especially for cast-in-place elements in 1810.3.9.
This section ensures the structural integrity of the concrete elements themselves. Section 1810.3.9.1 introduces the concept of the design cracking moment, or M sub CR.
And there's an equation for this?
Equation 18-5. The designer uses it to make sure the pile or shaft maintains its integrity and doesn't fail catastrophically when it's subjected to bending forces from lateral loads.
And this leads us to the most stringent structural demands in the whole chapter.
The seismic reinforcement requirements in section 1810.3.9.4. This is for deep foundations in high seismic zones, specifically categories C through F.
Because seismic forces induce severe cyclic bending and shear on these elements.
They do, and it demands exceptional ductility and confinement. These are non-negotiable structural requirements in places like California. Minimum longitudinal and transverse reinforcement ratios are explicitly required.
The vertical bars have to extend a minimum length.
At least 1/2 the element length, but not less than 10 feet or 3 times the least element dimension. This special reinforcement has to be applied in zones where that design cracking moment is exceeded.
So the focus is on the area right beneath the pile cap, where the forces are highest.
Exactly. Within that critical zone, the transverse reinforcement, the hoops or spirals, must have very tight spacing, no more than 6 inches, within a certain distance from the cap.
And what does that tight spiral reinforcement do?
It provides the necessary confinement to the concrete core. It prevents it from spalling or shattering during a big earthquake, ensuring the element can sustain those critical load demands.
Finally, Section 1810.4 gives us requirements for specialized deep foundation systems.
Each one demanding specific construction and testing protocols. For instance, Section 1810.4.1 for precast concrete piles requires a high minimum compressive strength of 4,000 psi.
And Section 1810.4.5 covers timber piles,
which requires specific provisions for treating the timber against damage and dealing with decay, especially in marine environments.
There are also 2 highly specialized types addressed.
Right. Section 1810.4.9 discusses socketed drilled shafts, which are shafts embedded into solid rock. Their design requires a specialized analysis of the rock socket itself and the bond strength between the grout and the rock.
And the other one is micropiles.
In 1810.4.0, these are small diameter piles less than 12 inches. Because they're so slender, they rely on friction over a great length and often use high-strength steel, requiring very specific installation and testing methods.
Wow. We have covered a tremendous amount of ground today, literally.
We have. Chapter 18, Soils and Foundations, dictates the entire sequence of events from the required geotechnical investigations in 1803.
Through the safe preparation of the site, with excavation and grading in 1804, setting standards for moisture protection and presumptive loads in 1805 and 1806.
Detailing the structural walls in 1807, and finally, establishing the rigorous requirements for both shallow foundations in 1808 and 1809, and the engineering complexity of deep foundations in 1810.
So the key takeaway for you, our listener, especially if you're studying for an exam, is that getting good at Chapter 18 is all about efficient navigation.
It's knowing when to use the prescriptive values versus when engineering analysis is mandated.
If a question gives you a soil type,
you go immediately to Table 1806.2.
If it gives you a simple house size and no geotech report,
you jump straight to the easy sizing chart in Table 1809.7.
And if the word seismic or high-rise shows up,
you know you are immediately diving into the rigor of Section 1810.
It's truly the chapter that dictates everything that follows structurally.
It is.
And that brings us to our final thought for you to consider, which I think ties the whole chapter together. When is it more beneficial, not just legally required, but truly beneficial from a safety and long-term cost standpoint, to skip the convenient, conservative, presumptive values in Section 1806 and instead mandate a full, expensive geotechnical investigation?
That's a great question. And the answer really lies in value engineering. While the presumptive values are safe, they're often overly conservative.
Meaning they make you build bigger, more expensive foundations than you might actually need.
Exactly. The site-specific data you get from a detailed geotechnical report, especially on a large commercial project, often allows the engineer to utilize the soil's capacity far more efficiently.
So you can ultimately reduce the size and cost of the foundation system,
while at the same time increasing safety by identifying and mitigating hidden hazards like liquefaction or expansive soil. The code is really nudging you toward investigation for a truly optimized design.
A fascinating insight into the engineering economy behind the code requirements. If you found this navigation helpful in cracking the code book, please consider supporting the Code Navigators and helping us create future content.
You can find the Patreon link available in the show description.
We really appreciate the support.
Thank you for joining us on this critical session exploring the Earth's response to our structures.
We'll see you next time as we continue to guide you through the International Building Code.